Cool today. It'd be a nice, easy Friday presentation about what it was like for me living in Christchurch after the Canterbury Earthquake Sequence. So we'll talk about, as you said earlier, we'll talk about the earthquake sequence, uh, some of the challenges with the rebuild, and then very briefly we'll talk about foundation strategies for liquefiable ground. New Zealand is a really interesting place. Most of the 5 million population is on the North Island in Auckland. Christchurch area has about 400,000 people. Of course, they filmed all the Lord of the Rings and the Hobbit movies there, and you can go to Hobbiton, the movie set, which we did, and that's one of my hobbits there. He's now taller than me and applying to university. He's a senior in high school now. I have another one who's off somewhere throwing a tantrum, which he did for every sort of family outing forever. So he's going to be 16, and we're learning to drive for him this summer. So things grow up. Kids grow up fast. In fact, I can't believe it's been almost 15 years, and I'm still talking about this experience. But it was really a transformative experience for me and my family. And if you ever have a chance to go move and work somewhere in a post-earthquake sense, then I really recommend it. Of course, Christchurch was a very easy place to relocate to. There was lots of exciting damage and challenges in the rebuild, but there was still quite a functioning city. So that was a really good opportunity. So some funny things about Christchurch. It feels like everybody there has a brand new house, or at the time when we were there, everybody was getting a brand new house, and you'll know why in a few minutes. Everybody knows about geotechnical engineers. I've been in the business now 26 years or so, and for most of my career, when people ask what I do, I say I'm a civil engineer. It's a lot easier to explain that than geotechnical. But in Christchurch, everybody knows about geotechnical engineers. And even the guy at the gas station, I'm not kidding, our first week in town, the guy at the gas station starts telling me about liquefaction, which was just unheard of. That somebody else besides our nice, tight inner circle of earthquake engineering knows about liquefaction. And then something very special about New Zealand is they have a national natural hazards insurance. It's run by the Earthquake Commission, or EQC. It covers earthquakes and landslides and any sort of natural disaster. And this is a really important point because a lot of the rebuild effort is funded by this insurance, and we got to do things as part of the rebuild that I don't think would have been possible without having that national insurance. So here's New Zealand, two islands, the North Island and South Island. Of course, Christchurch is on the South Island. You can see in the picture, let's get my pointer up, that there's something going on offshore up here. So of course, this looks a lot like where I live in Seattle. This is the Hikurangi subduction zone. So you got the Pacific plate sliding underneath the Australian plate. So up here with lots of volcanic activity, just like in Washington, very similar. And then we have this big strike slip fault called the Alpine Fault down that goes through the South Island. So this thing is cruising along. And of course, beneath that, there are lots of unknown faults and other faults. And the whole place is in a very seismically active area. So we'll talk about Christchurch. Of course, you might have heard of the earthquakes in Kaikoura that happened in 2016. I won't talk about those today, but certainly have some experiences from that as well. And like I mentioned, Auckland's the big city up here. Wellington's the capital, right in the middle at the southern end of the North Island. So the first earthquake in the sequence was the Darfield earthquake. It was a magnitude 7.1 earthquake that happened out about 40 kilometers west of Christchurch. When you get a big magnitude earthquake, it's going to rupture a larger part of the Earth's crust. So usually when we get magnitude over about 7, we start seeing evidence of the fault rupture at the ground surface. And certainly that was the case for the Darfield earthquake. So most of the photos I show you today are mine. Some of them a lot of them I took off the internet. I don't think I did a very good job at referencing them. So if you're interested in anything, let me know and I'll dig them up. But certainly, anyway, the slide here shows evidence of surface fault rupture. This aerial photo, you can see quite clearly the fault rupture in the farmland. If you look really closely at the upper picture, you can see the top of the hedgerow kind of has a shift at some point. So the elevation's a little bit higher to the left than it is to the right. And what goes along with that hedgerow is this drainage ditch that I saw. And you can see the drainage ditch has got a new bend in it. It doesn't used to run straight. So, I mean, these are really cool, fascinating things about large magnitude earthquakes. And of course, I wasn't the first one out there taking pictures. This was in the forest area just across the road. It says the quake was last year. Get over it, move on, leave us in peace. So this was in February of 2011, so a few months after the Darfield earthquake. So I wasn't the only earthquake tourist to come around there. There are definitely more of us. So we had this big magnitude 7.1 earthquake, and then a few months later, we had the big one. And the big one in this case is the magnitude 6.2 Christchurch earthquake. This was February 22nd, 2011. And we had this nice cathedral in the middle of town, and the cathedral came through the Darfield earthquake just fine. But after the Christchurch earthquake, you can see the big tower has collapsed, and we're gonna dive into some of the reasons why here in a bit. So why do I call the magnitude 6.2 earthquake the big one, or conversely, why isn't the magnitude 7.1 earthquake the big one? Well, the reason is quite clear here. The Christchurch earthquake was very close to Christchurch Central Business District. And we have to remember, even though we're earthquake engineers, we actually don't design for earthquakes, we design for ground motions. And so the ground motions caused by the smaller magnitude but closer earthquake were much more intense in Christchurch than the ground motions that came from the Darfield earthquake out to the west. So we have to remember, earthquake engineering, we get really focused in what's going on in the soil, what's going on in the structure. But the reality is that it's a very large system that we're all working with. It starts all the way with fault rupture. So we like to say that the earthquake engineers that forget that geology and seismology are important are really just vibration engineers. Not to be offensive to actual vibration engineers, but I would say to all of you, don't forget that we've got a big picture that starts at the fault, and go out and be an earthquake engineer. Don't be a vibration engineer in your career. So for me as a geotechnical engineer, most exciting thing is liquefaction. And when I got to town, I saw lots of areas that look like this. It's a rugby pitch covered with sand and silt. Different parts in town were covered with sand and silt. And it happened more than once in several times during the earthquake sequence. So this is all this soil and water has been forced up out of the ground because of liquefaction, and made quite a big mess. So if you don't know a lot about liquefaction, here's an example that I think you can relate to. If I can figure out how to. No, hold on here. Let's see if I can get my clicking back. There we go. So you've all been to the beach and you stood at that part of the beach where the waves have come up and the sand might be saturated, but it's still quite firm. And I bet you've wiggled your toes around, wiggled your feet around, and you're able to make the soil looser or the soil softer. You can make yourself sink down in there up to your ankles. And that's exactly what this seagull is doing. Seagull is going around and tapping on the top of this sand, and what she's doing is she's causing liquefaction to happen at a very shallow depth. And as it's trying to bring up that soil and water that we saw in the previous pictures, here it's making the bugs that are just below the surface float to the top so she can get lunch. So this is just liquefaction on a very small scale. Of course, earthquakes make it on a very big scale. And I promise this will probably be all the soil mechanics that we talked about today. And if you're not familiar with liquefaction, and this will help you understand why the pore pressures increase when the earthquake happens. So you can take your knuckles and put your knuckles together just so that they're just touching, and pretend these are little pieces of sand. Let me get the pointer back. Right, and put them together as in the loosest configuration you can, just so they're touching. And then when you shear your knuckles, you see what happens. The sand particles try to collapse, try to fill in this void space in between. So they want to become more dense. And this is fine until we put water in the pore spaces. When the water's in the pore spaces, it obviously doesn't want the sand particles to become dense because it's already occupying that space. And if there's not enough time for the pore pressures to redistribute and the water pressures to move around, then they're going to take on excess pore pressure that will try to resist this shearing movement. And that would be exactly why bugs will come out of the ground when the seagull pats the top of the surface. She's causing pore pressures to develop because she's shearing the soil. Now, we usually think about this as being a phenomena that happens with loose, clean sand, recently placed fills, dense sand that's already compact, where you're already dense, doesn't build up pore pressure like this. Generally, plastic fine-grained soils like silt and clay don't, although there is now some evidence that they do after a lot of shaking. But you won't go wrong generally thinking this is a problem for loose, clean sand that will develop liquefaction. So we'll talk about how the soil got to Christchurch, and you'll start to understand why liquefaction was a problem. So Christchurch sits at the end of what we call the Canterbury Plains. So here's that big alpine fault that I was talking about, and it's built up the mountain range, the Southern Alps, and over time the different sediments have been transported down out of the Alps and deposited in these cool braided rivers all across the plains. These rivers have moved around over time. They're not always in the same place, but they're really fantastic. The watercolor is amazing in New Zealand. You get green and blue, and they're just a really neat place to go look at geology and nature. Over time, when sea level has gone up and down, it changes how the material gets deposited as it's coming across the Canterbury Plains. You can imagine when the river is bringing down boulders and rocks and sand and clay. As soon as it empties into the ocean, the heavier materials like the boulders and the sand are going to drop and be deposited first, and this lighter fine grain material will be transported further out. So what we have is, over time, when the sea level has gone up and down, we get these fingers of gravel being deposited. So when the sea level is really low, the gravel can get transported further, and when the sea level is really high, the gravel drops off sooner, and the fine grain material gets carried out. So current day Christchurch sits right across an area where off to the west we have generally gravel soils. In to the eastern part of Christchurch, we've got fine grained sand, silt, and clay. So I said earlier, gravel is probably not something we worry about for liquefaction, but sand, clean sand, is something that we're going to worry about. So keep that in mind. East part of Christchurch is where we expect to find liquefaction. So a few pictures of the types of things that I observed in when I got to Christchurch. Uplift, we already talked about bugs coming out of the ground. Well, here's a manhole for a sewer that's been popped up because liquefaction has happened underneath it and the pore pressures have pushed it out of the ground. In this picture here, this is an underground parking structure, and that's about 150 millimeter thick or height of uplift. So the entire parking structure has shifted and tried to come up out of the ground. Yeah. Lateral spreading, I won't talk too much about this today, but it's another liquefaction induced phenomena where if you've got a slope or a free face, like a bridge abutment, or there's actually a retaining wall to the right side of this picture. And if you look up here, there's a little river, so it's a slope down to the river. If you've got a free face like that, and the ground underneath liquefies, you can kind of see the crust of soil riding on top of that liquefied zone towards that free face. And these could be highly damaging to anything that we're building at the surface. There are certainly plenty of that around Christchurch. Retaining walls are something we all get involved with at some point. By and large, I think retaining walls did pretty well in Christchurch. There's a few things to point out that this happened a lot. So we've got this material. This is silty material that's been blown from the Canterbury Plains up against the hills to the south of Christchurch. It's called loess. That's the type of deposit. And this material itself is really strong until you get it wet, and then it's very highly susceptible to erosion. So a lot of these retaining walls aren't really retaining walls. They'll just be a facing that people put on the loess to prevent erosion from happening, and it'll self-stand by itself quite high. Among the retaining wall damage that I saw, crib walls didn't fare that well. A lot of them were damaged. Not many of them fully collapsed like this, but certainly a few of them did. What's kind of fun in this picture is when I first went to Christchurch after the big one in February. I walked around, took this picture, and you'll see a little sign up here that says tennis. That's where my kids eventually went and learned to play tennis, was just around the corner from this one. Cliff collapse, not something that we normally think about from an earthquake engineering perspective. Certainly our engineering geologist friends will be much more in tune with cliff collapse. But we had quite a lot of it in the earthquakes, and you can see, this picture here, we were just standing right up here and having a nosy around, and then we walked around and saw this big crack and thought, okay, they've given us a pass to walk around the city and look at damage, but we weren't being very smart from a health and safety perspective. Just because we were allowed to climb all over everything probably meant we probably shouldn't. Should have used a little bit more caution. So of course this happened. This was a cool school called Redcliffe School. Luckily the boulders came down. They didn't really impact the school, but they had to relocate the school to a different location. And it was that way until we left Christchurch in 2019. They had just finally decided, took them that long, 8 years to decide that it was safe to rebuild the school back in the same location. And so that, I think it might be complete by now. That was some years ago, but I think something to think about that we don't always consider when we're doing design work is what it's like in a post-earthquake or post-disaster situation. We're talking about disrupting this entire community for 8 or 9 years, losing their public school or their primary school. So there'll be a generation of kids that didn't go to Red Cliffs, even though they may live right nearby. We used shipping containers for all sorts of things. This is a road from the central business district out to the coastal suburbs. You can see there's a few workers up here. They're scaling and knocking off the big boulders and the loose rocks so that they don't come down again in aftershocks. And they stack up the shipping containers along the side of the road as a debris barrier or a catching mechanism for any future cliff collapse. So yeah, you'll see we use shipping containers for all sorts of things, but they make really good walls in a pinch. Rockfall in general was a big story in these earthquakes, and you can see here's some sort of fresh exposures on these hills up here, and all of these boulders have collected in this little bit of gully. Certainly one had bounced across the road here and taken out this stone fence. And you keep looking to the left, there's a big boulder, got very close to that house. There were a couple of houses that did get the boulder right through the wall, and these are the size of a car. These are big rocks. After the earthquake, every single structure had to be inspected by a structural engineer, and they left these placards on the buildings and residences. And you can see this one actually says yellow there because what started to happen, these had been up for several months. They all started to fade. So red, yellow, and green all turned into the same kind of pink or white. So it was something to think about if you're involved with a disaster recovery. The little things like the color of the placard you put up there, maybe make sure it's someone's remembered to write the color on it or somehow make it easy to understand what level of safety or access should be applied to that particular structure. The Central Art Museum was turned into the disaster recovery area. So we would come in and check in the morning, sign the health and safety sheet so they knew that we were there. This is the Christchurch Wizard. He came to town in the 70s. He doesn't really have a job. He's just sort of a local treasure. I don't know, kind of a living art establishment. He's done a few things over the years, like cast spells for rain, and just generally been a good spokesperson for the city. Very outspoken about keeping the heritage quality of the buildings. But that's him, the Christchurch Wizard. He checked into the health and safety desk just like the rest of us. Going around the CBD, you see lots of little bits of damage like this. These are commercial buildings, quite a bit of unreinforced masonry that, as you would expect, didn't do so well in an earthquake. This is a neat one of a picture of pounding. So you've got maybe a shorter, stiffer building here that's pounded up against this other masonry building, and you can see the facade and the outer walls have been not knocked away. So the shorter building has won this fight a little bit. And lots of buildings were damaged. These are some great shear marks on the columns of this building, and this is a different building that we went into, and this was one of the shear walls in the building. The structural engineers we were with thought this was fascinating. This actually scared me. I didn't like to be in the bottom of a dark building with a wall. I mean, the bits of concrete inside this rebar cage are just literally broken up into, maybe cobble size pieces, not attached to the rebar anymore. I mean, luckily the building did its, fulfilled its function. It didn't collapse, but certainly this wall is no good anymore. Two buildings did collapse, and that's where most of the casualties in the earthquake occurred. It's the CTV and the PGC buildings. I didn't put in the pictures of the collapsed buildings because I didn't feel like we really needed to see that. And of course, things we don't usually think about: non-structural damage. Certainly, there were a lot of fireplaces in Christchurch, and a lot of the fireplaces collapsed or fell through the roof or broke off. You can see that this February earthquake happened just around 1 p.m. So whoever was in this house had everything out to be making lunch at the time, and then left after the earthquake, and it didn't really get to come back until many months after that. And of course, all the commercial space in town was quite damaged, and they'll have a time going through all these bottles trying to find ones that aren't correct, I think. Christchurch town has got these great historical buildings from the 1800s and early 1900s. And, they don't want to lose the look and feel of the city. So this was fairly common to see the building facade being propped up. A lot of times we put shipping containers here as well. The idea is if we hold the historical facade together, then later on we can go back inside and retrofit and strengthen the foundation and the structure. This is another good one. It's Oxford Terrace Baptist Church. It was damaged quite a bit after the Darfield earthquake. And I think the story I like to tell myself is it was damaged. So they put up this sign that said, "Our building is cracked, the church is fine." And then the Christchurch earthquake happened, and now the building is more than cracked. So lots of neat things to think about there. One is, certainly this is something that happened progressively. There was one earthquake that caused some damage, another earthquake that finished the job, but also going back to the idea that we designed for ground motions, not for earthquakes. That second earthquake made stronger ground motions that needed to be resisted by the structure here. And of course, it was in its weakened state. It wasn't going to happen. So we don't often deal with aftershocks, although it's not necessarily that the Christchurch earthquake was an aftershock, but the same idea applies. It's two earthquakes back to back. Of course, we saw that happen in Turkey just recently. Instead of being several months apart, though, those earthquakes were very close together. I'd say a lot of time in the dams world, certainly we talk about what happens if there is a second event. But for most of our design work, we're just designing for one ground motion and not considering aftershocks. So this is a map of all the broken water and sewer mains and submains. And the shaded areas here are areas with mapped occurrences of liquefaction. So not surprisingly, I think that most of the damage to the shallow utilities happened on ground that was liquefiable. Of course, liquefaction is very damaging to surface foundations and near surface utilities, and this really should be no surprise. I think the good thing is, in thinking about what your job might be in the future, is that, well, if you already know ahead of time, and we pretty much do, where liquefaction is most likely to occur, then you can be ready with designing a sewer system that is better equipped to deal with this type of damage. So in this case, flexible pipe did better than cement pipe. So that would be a good thing to keep in mind. Also, for your future reference, think this is a town of 400,000 that we're currently having to do 40 repairs to the utilities a day for about 3 weeks to really turn the corner. Of course, this is a plot of a frequency of repair to the system over time. Again, it's not something that we usually have to think about in our design jobs, but for our resilience planning, how do you ramp up from a regular workload to having to do 40 repairs a day and sustain that for a long period of time? That's a big challenge. After this experience, the city council did some thinking about what sort of goals they wanted to have for bringing back service if there was another disaster. And I like this chart, even though I don't really think about it in my everyday work, but for the same idea of, if there was an earthquake here, the goal would be that 90% of the houses would have service back within about 2 days. And that seems very optimistic to me. I think if I were to live through an earthquake like the Christchurch one again, I could probably understand if it took longer than 2 days. But certainly that's a great goal. I'll point out one down here about getting the water treatment back. So here they've said water treatment not causing adverse environmental impacts. Their goal is 3 months or full consent compliance in 6 months. Now that one is, in particular for me, is important because we first stayed near this beach. This is the town of Sumner, and for the first at least 2 years that we were there, what they had to do because of the pollution control plants in town were damaged, they had to reroute all the sewer out into the ocean. So there were signs up everywhere saying, don't go in the water. We're still pumping sewage. And that took them a couple of years to get those signs gone. So definitely longer than 3 to 6 months. But it was too bad. This was a great place. We spent a lot of time with our kids out on the beach here. There's a good playground and place to get ice cream out over here at the end. So I think if they could make it work in 3 months in the future, that would be fantastic. Some other things to think about. If this is a Google Earth view of the CBD before the earthquake, and you can see after 1 year, I'll just go back and forth. Lots of buildings are gone. So like I said, the buildings were designed for a non-collapse design criteria. Other than the 2 buildings that I mentioned, everything performed and according to that design target. But most of them were so damaged that they couldn't be reused afterwards. So they were deconstructed. Now we didn't say demolished because that sounded too negative. So we used the word deconstructed. So we started taking down all these buildings. And after 3 years, you can see, we're just kind of going back almost, a majority of the central business district now is being deconstructed. And this is going on for 3 years now. So by the time we get to 4 years, things are starting to happen. First of all, this is a new bus station that came up. It's really great because our office was here, so I could take the bus and just go right to work. But you'll see there's new construction, cranes starting to show up, and there's parking lots everywhere. So all this empty land became parking. Most of the time it was free until the local parking companies decided to start charging for it. But you never were lacking for a parking spot. We really wanted to have a central city feeling again. So we built this thing, the container mall. And so you can see another use for containers. All the local businesses had pop-up shops in these in these containers, and you could go get coffee and food and do some shopping. And so it was a way that people would be able to come back and use the central city again. So moving on, after about 6 years, we're starting to see things happen. So let's see if I point out this area here, that one's kind of where the first building started to finish in 6 years. We get some new shopping and new office buildings here, starting to fill in all the way up here. By the time we got to 8 years, it started to feel like a city again. Most of these new office buildings were getting occupied and people were coming back to work. But there are certainly other parts of the city off to the east where construction hadn't started. And when I left New Zealand and we were in the process of doing design work for the new stadium that's going to go right here, that is under construction and going quite well right now as we speak. So life in Christchurch was pretty much this for the 8 years that I lived there. High vis was a fashion statement. There were so many workers and cones and fences up. You never knew what part of the road was going to be fixed on what day. So your drive or your path in across town was always different. Sometimes they'd be fixing the road multiple times. Either they dug up one utility and fixed it, but didn't fix the other ones at the same time. Who knows? But you got used to always having some sort of traffic disruption. I know I'm running short on time, but we'll see how far we get. And I think maybe I'll stop just after this next little bit because there's some neat things that I want to show you still. So in moving on from the earthquake, now geotechnical reports became a requirement for any new residential construction in all of these areas that are highlighted here. So that's one reason why everybody knows about geotechnical engineers in Christchurch. We created a database. So all the local consultants pitched in their borehole information, their cone penetration test data, and it's still going now. You can go sign up for free, the New Zealand Geotechnical Database, and you can go in here and pull this data. And this was to help with the rebuild. And you can see here, most of the data at the time I made this picture is kind of clustered in this area. And hopefully you can remember back a few slides and understand, why aren't we collecting data out here to the west? Well, remember out here to the west was the area with more gravelly soils where liquefaction didn't occur. So obviously all the data that we collect is in the areas where there are problems. So I think that's kind of a neat way of seeing the effects of geology in our everyday life. Of course, we bought this house over here and in an area that was badly damaged by liquefaction. So the house was fairly cheap, but because I'm a geotechnical engineer, I could pull all the data and promise my wife that our particular lot was going to be okay in the future. So yeah, neat uses of the database. So we put everything else on there. So a study of peak ground acceleration in all of the earthquake sequence. So if you were doing some forensic analysis or you wanted to, back calculate or check something, you could go on into the NZGD and get the PGA value or likely PGA value for your particular site. Things like elevation changes were documented on there. So you could start forming a picture of how your site might behave in the future, looking at these. A neat thing to look at here is that the positive elevations, so vertical change, the green areas are down here in this southern part of the city. When we remember that the Christchurch earthquake, the big one, was a reverse fault. So this hanging wall, this block on the right side, is actually the southern part of the map. Shifts upwards in this fault rupture. And that's one of the contributing factors for the fact that the ground elevation increased in the earthquake. The other areas, the ground elevation has gone down for also a variety of reasons. In some areas, we had more than a meter of settlement. So that's the pink area. This is in what we term the red zone, the ground that was the areas that were so badly damaged that city council made a decision that they weren't going to support rebuilding back there. So no, they weren't going to try to put in new utilities or roadways, just because the possibility of damage there was so high. The risk was quite high. We did lots of walking around with our different damage assessments, writing down, documenting ground cracks. So you can pull up the ground cracks map on the NZGD, get an idea of, oh, look, this area has had a lot of maybe lateral spreading or lateral movement in the past. Again, this is the red zone. And as we expect, most of the ground cracks tend to follow the rivers here. But you'll see strange patterns out here. And if you dive down into the historical geology, you might find that there were buried channels or different geologic features that could explain other patterns in the ground cracks. Of course, horizontal ground movements. So you can see the ground displacement vectors, and just another before and after. This is the red zone before the earthquake, and again, here it is after. Lots of deconstruction happening in this area. Like I said, nothing's going to go back. This picture on the left are all the students from the University of Canterbury. They made what they called the student army that came out and cleaned up all the sand and water ejecta. Eventually, the farmers came in from the Canterbury Plains with their big yellow pieces of equipment and took this sand and this mess and hauled it away. So the student army handed off to the farming army, they called themselves, and that was the way the community got things done. This article up here, engineers leaving reports unsigned. This was actually us. I worked for a company called Golder at the time. What we found was that everybody was due some sort of recompensation from the Earthquake Commission for their natural hazard insurance. And so a lot of work went in to collecting data to help people quantify the amount of ground damage that happened as a result of the earthquakes and liquefaction. Well, there were a few people that were not happy with the settlement that they were presented with from EQC, and they became really quite pains in everybody's ass, to be frank. So to the point where people would take a geotech report that we might have done at Golder, read through and find the names of the engineers that were just doing this report for the insurance company, and start calling and harassing them. So we had a lot of young, brand new staff engineers get harassing phone calls from people unhappy with their claim. So we just said, fine, we're not gonna sign the reports anymore. And so this headline was because of us. Eventually, only I signed reports, or another fellow named Clive signed them, because we were old enough and to defend ourselves, I think. One of the other neat things is that Golder was a lot of fun. It was a really fun place to work. And so we saw an opportunity. We bought a CPT machine that came to New Zealand from Kansas. So you can see we named it Dorothy. And so we ran around, and our young geologists and young engineers learned how to do CPTs. And we went out and used this all over the place. At the time, as part of the rebuild, every new home would get 2 CPTs. And if you've ever done any residential or site development, 2 CPTs for a single house is absolutely crazy. We might do 2 CPTs for a big block of houses. But here it was part of the rebuild, part of understanding the insurance claims. So for us, it was a good business opportunity and a great experience for our young engineers and geologists. And the last piece of this is, now lots of people like me moved to New Zealand after these earthquakes. We had an office that was filled with people from all over the world. It was just a really amazing work environment to be in. Um, the problem was that not everybody came to New Zealand with a firm understanding of liquefaction. And what we started to get was that every company, every engineer would do things a little bit differently, some closer to the right answer than others. And it got to a point where the government had to step in and write up a set of guidelines and say, look, we got to get everybody moving in the same direction quickly. So we made these guidelines. The guidelines provided, some methods of analysis, ways of assessing the site, and ways of assigning foundation options to deal with the ground conditions. So you can go download these guidelines if you're interested, but it's pretty dry reading. But it was the only way of getting everybody going in the same direction. Now, I don't know what you all think. I think we're only scheduled till 1. I've got a few more things, but if you've got questions now, we could stop here. What's everyone think about that?
Continue the presentation, James.
Keep going.
Yeah, keep going, please.
Okay. All right. I'm close to being done. I promise. So we'll talk about the last bit here, and I'm not going to give you a full detailed engineering guide, foundation design guide, but I'll tell you about the kinds of things that we were thinking about when we were doing our foundation designs on liquefiable ground. So, of course, when liquefaction happens, when an earthquake happens, there are lots of different mechanisms for the buildings to settle. We talked about sand and water coming up out of the ground. So this ejecta itself can create large localized settlements. Of course, lateral spreading that is trying to pull the ground apart, that makes big settlements. But also when the ground is liquefied, it loses some of its shear strength, so you can get bearing capacity failures, and the action of the building rocking around during the earthquake can help it work its way into the ground. So these are these are all really complicated things, very difficult to handle if we're just doing, let's say, a residential structure or even a smaller commercial structure. We're just not paid enough or given enough time to work out detailed solutions. And that's one of the reasons why the guidelines were created. So somebody has already done some thinking about if your site conditions are one way or the other, here are some types of foundations you can use that would address these different mechanisms. Now, I've taken everything in the guidelines and I've broken it into 3 types of foundations. Very easy to remember. There's the princess strategy, there's the pirate strategy in the middle, and then Mighty Mouse. Now, when you think of the story of the Princess and the Pea, if you all know this story, the general concept was, they were auditioning would-be princesses, and they only wanted the princess that was the most sensitive, and so they devised a test of putting a pea underneath a stack of mattresses, and if the princess slept on the mattresses and was bothered by the pea, then you knew that she was sensitive enough to become the next princess. So I like to flip this on its head and say, well, how many mattresses then would we need to stack up before the princess stops feeling the pea? And that is what I call the princess strategy when we're talking about liquefaction. So this is backed up. This is a well-known concept started by Ishihara in the 1980s. Walked around after some earthquakes, wondering to himself, "Oh, I know liquefaction happened in this location. Why didn't it happen here?" And he identified that if liquefaction happened down very deep, it didn't cause damage at the ground surface or didn't leave evidence. So he had this idea of, looking at the thickness of the unliquefiable surface layer. We might call that the crust, or a non-liquefiable crust. I like to think of it as the number of mattresses we need to stack up. So if we have a lot of mattresses or a very thick crust, we can resist the damage, some of the types of damage due to liquefaction. So the way we tackled this in Christchurch was we did a lot of ground improvement. And the idea for the ground improvement was to build a mattress of a suitable depth and a suitable area that we could feel confident that we would suppress some of the more damaging types of liquefaction damage our building settlement mechanisms. This was another fun thing with Golder. We had a CPT rig, and then we partnered with a GeoPier contractor, and we ran the GeoPier franchise for a while, installing rammed aggregate piers. So we did a lot of design work for those. So that's the Princess concept. And if you don't believe me, let's go back to this picture. This is the LiDAR, the vertical elevation change. And you'll see there's this line here of orange and yellow. This is a main road. So of course, when we go out and build a road, we're gonna put some base material in, we're gonna compact the ground surface. So we're gonna make the ground surface underneath the road just a little bit better than the surrounding areas. And here's some, I guess, evidence that near surface, what we do near the surface makes a difference, because the road itself didn't settle as much as the surrounding ground. The pirate strategy, the idea here is you make the foundation really stiff. So like a pirate ship that's out on the waves. When the waves come, the waves might rock the ship back and forth, but the ship, it stays together. So we can take that into our foundation design. We started building these waffle slabs. So it's a kind of a reinforced slab foundation with a perimeter footing and these ribs of concrete in between. So this was a much stiffer foundation than just a typical slab on grade, or some of the other normally used options in Christchurch. The idea here was, well, if the ground settles, if there's liquefaction in the future, the structure itself will stay together like the pirate ship. And it'll take some work afterwards, but we can probably go back and fix it. That's the concept. And then the last one is the Mighty Mouse strategy. So this is an idea where there would be two slabs cast together, and you can see that in the right. And then throughout the top slab, they will pre-install points to come back in to jack the slab up if settlement happens. So we've built in a mechanism to re-level the foundation. Usually these would also come with some sort of ground treatment. So very common to have, a 2 to 3 foot thick reinforced gravel mat underneath the double slab option. Makes it very expensive, but you've got a lot of resilience for going forward. Let's see, I think we're almost there. And I bring this up because I've had a lot of experiences lately using our ASCE 7 code, where we are designing, the purpose of the code has got some collapse functionality to it. And so we use the ground motions from the code to do a liquefaction assessment. And what I see is that a lot of people, even though we're designing for collapse, still want to get a really tight settlement performance out of this from a liquefaction standpoint. And I don't think that's the right way to do it, because if liquefaction is going to happen, you're going to have more than a little bit of settlement. So I really liked what was done in New Zealand. We considered two different ground motion levels, an ultimate limit where everybody understood that there could be more than just a little bit of post-liquefaction settlement, but that's okay because we're just trying to keep building collapse as the design criteria. But then we also do a serviceability check where it's a smaller return period ground motion, so something that's more likely to occur in the building's design life. But we try to be really careful that we're not going to get large settlements that would be cause significant damage. And I like that two-tier approach. There are a lot of things that I didn't cover. I won't list them now. And my final thoughts here. Going forward, if you're ever in a position to prepare for a disaster, the things that I think are most important is that know where all your data is or how to find it. Or better yet, start a database and address data gaps now, not later. Like I said, we can predict where the sewer and submains ruptures would occur because we know the geology. We know where the liquefaction is most likely to occur. Have put some time into training your disaster response. In New Zealand, people weren't prepared. After the earthquakes, the government started a program of certifying structural and geotechnical engineers through a disaster response training. For the next time, now they've got a number of trained engineers that know the types of things to look for and how to properly placard the buildings. And of course, if you getting everybody on the same page for how you want to do your design on liquefiable ground is really important too. And you can't have enough cones, fencing, shipping containers, or porta potties. I tell you, there was a porta potty on every corner for a few months in Christchurch because, again, all the sewer system was not functioning. And my last slide is, one of the neat things about having a national insurance program is that they had a lot of funding to do some things to help optimize the recovery. So one of the things that happened down in Christchurch was a blast-induced liquefaction trial program to test the different types of ground improvement that were being used. So this was in an area in the red zone. And let me hopefully play the video. I don't know if you can hear it, but it's one of the blasts here. All right. Yeah, it was that was cool. We were one of the panels here. We had our rammed aggregate piers underneath one of the panels. And I think in the end, the rammed aggregate piers worked the best than all the other ground improvement methods. But it took so long to release the science report documenting the outcomes of the study that we had pretty much finished putting ground improvement in around Christchurch anyway. And that's it. So thank you.
Thank you very much for that insightful presentation, James. Well, now we'll open the floor for questions. If you are here in person, please raise your hand and we will invite you to speak. For those joining us via Zoom, feel free to type your questions and we will read them aloud, or you may unmute yourself to ask directly. Please.
Can you go over that example at the end again? What exactly was going on there?
This one, is that what you mean?
Yeah.
Okay, we funded the EQC funded a study of blast-induced liquefaction. So we set off panels of explosives all around this area in the red zone to assess which types of ground improvement were most effective at mitigating the effects of liquefaction. So this was one of the blasts, one of the blasting days, and I'll play it again. So under each one of these panels is a different type of ground improvement. And we're looking to cause liquefaction in the ground and then see which panel had the least amount of differential settlement.
those was the best one you said.
Can you repeat that again?
Sorry, you said that one of them performed better than the other ones. Which one was that?
Oh, the geo piers, the rammed aggregate piers.
Please go ahead.
Thank you so much for the presentation. Why did you end up leaving New Zealand in 2019 and came back to the US?
That's a good question. I think everyone in my family agrees. We wish we were still there. It's a great place to be. We loved living there. The kids loved growing up there. But we had this idea that the kids might want to go to university in the US, and we probably should have some tighter relationships with their grandparents. So we came back when my oldest was just going into eighth grade here, and it was a good time. It was a good opportunity to relocate to Seattle. So we came back for family, but yeah, I think we left all of our hearts in New Zealand for sure.
Another question is, what got you into geotechnical engineering and ended up coming to New Zealand for this? Was it for this project, or was it for, like, did your company offer you the opportunity to basically come to New Zealand and study the aftermath of this earthquake?
Yeah, look, the origin story is a little different. We after our second child was born, we realized that now with a family of four, it was going to be too difficult and too expensive to ever travel and do and see some of the world. So we had this idea and knew some people that were in Australia, and Australia was booming with the mining industry. And they said, yeah, come on down. So we actually moved to Sydney in 2010, right at the time when that Darfield earthquake was happening, just about a week afterwards, as basically a permanent family vacation, just to see what it was like living somewhere else. And then the earthquakes happened in New Zealand, and we had some opportunities to go over to help out with site inspections and the initial parts of the disaster recovery. And we realized that we actually liked New Zealand, Christchurch, a lot more than Sydney. And then looked for a job to come across from Sydney to Christchurch, and that was that.
Thank you very much.
Yes.
Thank you for your presentation. I was just wondering, in terms of codes, I'm assuming that it's very different between the codes in the US and New Zealand. So do you feel like it was easy to go back, like back and forth between the two, I guess? It was like when you came back in the US, was it hard to go and use a different code?
Look, I mean, I tend to try to resist using a building code whenever possible. Maybe that's the geotechnical engineer in me, is that a lot of what we do, yeah, there's some code for it, but most of it is just going to be good engineering practice. That's not 100% the case, but I would say I don't know. What am I trying to say? I have a great disdain for codes. I find them confusing and suffocating. And I won't say I've had an easy or a hard time going back and forth. I just don't like any of them.
Suffocating is a really good word.
Yeah, yeah.
We have time for one more question. Okay, please.
All right, thank you for the presentation. I think it gave a good, perspective of how, what the recovery looks like. after a major earthquake. So just one quick question related to what you showed about that school built just by the landslide. So what's your opinion about the level of preparation in terms of urban planning to a major earthquake based on what you observed after the Christchurch earthquake, the major one?
Can you
So-
can you say I got to stand a little bit closer to the speaker so I can hear you a little bit better. Can you repeat that again?
Oh, sure. Can you hear me now?
Yeah.
Better? Okay. Now, so my question is, based on your experience of what you observed overall, what do you think was the level of preparation to this major earthquake in terms of urban planning? And I'm referring, for example, to that picture that you showed of that school just by the landslide. So you think in general it was a good understanding of the potential risk and, kind of consistent urban planning or not?
No, and I don't know for sure, so I'll just say from my observation, I don't think the urban planning considered natural hazards a great deal in Christchurch. I mean, the city was founded on a swamp, on swampland, on just about the worst soil conditions that you can imagine. People love to go live up in the Port Hills. I know I lived up there for a while, and there are lots of natural hazards. There's erosion and piping issues with that loess. There's the cliff collapse and rockfall hazards. I don't think that people considered those very carefully. Now, the funny thing is, and I don't think this is a slant on New Zealand, because I think this will probably be the case anywhere in the world. Everybody at the university and the New Zealand GNS, their geologic survey, they were quite well aware of the liquefaction hazard, of the rockfall hazard, cliff collapse hazard, and they have been doing research and publishing papers and reports for long time. But it took something like this to really open people's eyes. And I think, like I said, I don't think that's just a problem unique to New Zealand. I bet you that's the case in most places.
Thank you.
You're welcome.
Well, that brings us to the end of today's seminar. A big thank you to Jens Mismiuk for sharing his expertise with us. We also want to thank you all for attending both in person and online. We look forward to seeing you at the next EERI Friday seminar. Thank you.
Great. Thanks for having me. Look, I'll next year or next time I'll make sure we get up there. Just didn't happen this year.
Sure. Thank you very much.
No problem.